Hey, I just wanted to quickly plug that if you guys want any tutoring, some new slots have opened. If you look in the description, there's a link to my physics and maths tutor profile in which I do tutoring on there. Hello everybody, welcome back to another episode of the A-Level Cookbook. Today we're going to be doing the OCR A-Level Chemistry A paper from 2021, and this is paper 3. So let's get started. So these short questions are from different areas of chemistry. So a flask contains 110 grams of CO2, 120 grams of O2 at a pressure of this. What is the partial pressure of the CO2? So the partial pressure equals its mole fraction times the total pressure, right? So we have the total pressure here, but we need to find out its mole fraction. So what we need to do is we need to work out the moles of everything, because the mole fraction equals the moles of gas that you want over the total moles, right? So then we need to do the moles of CO2, which if we do that, we get 110 mass over its MR, which is 44, and that gives you 2.5. And then the moles of the O2, which is going to be 120 over 32, which is roughly 3.75, right? So then the mole fraction of the CO2 is going to be this 2.5 divided by the total moles, 2.5 plus 3.75, right? Which should give you 0.4. So therefore, its partial pressure is its mole fraction, 0.4 times the total, which is 50, which gives you 20 atmospheres. Done. Pure PCl5 is placed in a sealed container, which is heated to 200 degrees. An equilibrium is set up where PCl5 becomes these two. Fine. Under these conditions, Kc is this, the equilibrium concentration is this. Calculate the concentrations of PCl3 and Cl2 at equilibrium. So write down what you need to use. So we're going to be using this Kc, so we need to write an expression for Kc. So Kc is going to equal the concentration of PCl3, not the partial pressure, because it's K, where is it gone? Kc, not Kp, Cl2, I know it says gaseous, but you can still use Kc for gases, all over PCl5, right, in its concentration. They want you to find the concentrations of this and this at equilibrium. Fine. What we need to do is we need to rearrange this, and we might be able to get somewhere. So here, let's think about what's happening. This will have had some certain amount, right? Some mysterious amount x, and these are 0 and 0. At equilibrium, when you've left it to reach equilibrium, this will have gone down by x minus y, some mysterious amount, and these will have gone up to become y, right? So if we had 10 here, for example, and then the question's equilibrium, it was 5. That will have gone down by 5. These will have gone up by 5 and 5. Because they're in the same volume, therefore, the equilibrium amounts, moles, of PCl3 and Cl2 actually have to be equal to each other, right? Because we're assuming that this equilibrium started with 0, and the questions also told you that we had pure PCl5 in a sealed container, meaning there was none of these to begin with. So because they're in a 1-to-1 ratio, if one of these dissociates, then you're going to get one of these and one of these. So therefore, I can rewrite our Kc expression really as Kc equals the concentration of either one of them, so I'll just say PCl3 because they're equal, squared over PCl5 concentration, right? So then if I do Kc times PCl5's concentration, I'll get PCl3 squared, right? But if I just square root that, then I'll get the PCl3. So always write your working out first and then put the numbers in. Otherwise, a miserable examiner who's had to read through hours and hours and hours of garbage is not going to go and look and be like, oh, this person deserves a mark here. So that means that the concentration of this PCl3, now putting the numbers in, would be the square root of Kc, 8 times 10 to the minus 3, times the concentration of the PCl5, which they gave you, 0.05. If you do that, you get 0.02 moles. There you go. So the electronegativities of HC, N, and F and the boiling points of methane, ammonia, and hydrogen fluoride are shown below. So we can see that H has got pretty low one, C is marginally higher, N is higher, and F is really, really high. And then we've got our compounds here. So we've got CH4, which has got this boiling point here, NH3, which has got a higher boiling point, and HF, which has the highest. So then it says, explain the difference in the boiling points of CH4, NH3, and HF. So we need to think, when we're boiling these, what are we actually doing? We're not breaking covalent bonds, which is what surprisingly a lot of people say, right? If you're doing that, you're not having CH4 anymore. You're not boiling it. You're actually just getting carbon and hydrogens. That's not the same thing. We're not breaking that. What we are breaking are forces between these molecules, intermolecular forces. We need to identify what intermolecular forces there are. Now here, the electronegativities between C and H, although C is higher, generally speaking, we treat them as if they're the same. So here, the forces that we have are London forces, right? But we have nitrogen bonded to hydrogen. So that must mean NOF and H, remember? We have hydrogen bonds. And here is why we have hydrogen bonds, right? So now we're at a point where we could probably talk about the methane bit, right? We know that that's only got London forces, whereas these two have hydrogen bonds, which are stronger. So we can start by saying, well, CH4 is the lowest boiling point because it has weaker London forces which require less energy to overcome, right? Whereas NH3 and HF have hydrogen bonding there. But we still haven't really talked about the data they've given us here. What we can see is that the boiling point increases as you can see the electronegativity increases, right? And if HF has a higher boiling point than NH3, the only explanation for that, because the only things that really matter between them are the hydrogen bonds, it must be that this has stronger hydrogen bonds. There's no other way to explain it. That's the only fundamental difference. So here, HF has a higher boiling point than NH3, therefore it must have stronger hydrogen bonds. You could also argue, well, I mean, NH3's got more electrons. Why isn't that the higher boiling point? Well, I mean, the hydrogen bonds must be stronger here than it is in the London forces, and the hydrogen bonds here in combination. That's the only explanation that would fit the bill. Compound A has the following percentage composition by mass. A student reacts compound A with water to form an alkaline gas B and alkali C. Identify A, B, and C and write the equations for the compound A with water. So if we have a think then, so we can at least figure out what this thing is by using a bit of empirical formulary calculi stuff, right? Because here, okay, so with A, we know that it's got 81% calcium, this much nitrogen. So I'm going to write a Ca and N here, and I'm going to work out their empirical formulae. So 81.10 and then 18.90. If we do that and we divide it by the AR of calcium, one sec, it's going to be 40.1. And then here, 18.9, we're going to be dividing it by 14. If we do that, we get a ratio of 2.0224. And then for the 18.9, we get 1.35. Fine, so we need to figure out how to make this look good and eventually get a nice ratio. So if I times that by 2, we get what, 2.7? And here I do 2.022 times 2, that's 4. Still doesn't look too good though. That's not very close to a number. So we want to try and get really, really close. So I'll try times by 2. Let's see what happens if I times by like 3. If I do times 3, then that ends up being 4.05. And then if I do the CA2, this thing times by 3, then I'll get 6. So then that implies there's a 6 to 4 ratio. Lowest common multiple of that is going to be dividing it by 2. So that'll end up being 3 to 2. CA3 and 2. So at least we figured out what A is. Cool. We need to use the clues in the question. This compound A reacts with water to form an alkaline gas B, right? If it's an alkaline gas, we're going to be testing for it. There's an experiment we do where we, add sodium hydroxide, we heat it, and then we measure the gas, if that rings a bell, and you get ammonia. So that means B has to be NH3 on that principle. And then the other alkali C, well, we have to think about what that is. So we're putting this and we're getting it in water and we're getting an alkali out of that. So the clue here is that if it's alkaline, right, and it's a solution, it's got to eventually cause hydroxide ions to exist. This is the NH bit dealt with. Because if you react it with water, this N bit from here goes into NH3. So what's left is all the calcium bits. Calcium in water, something that's basic, has to be calcium hydroxide, like that. So now I know what B and C is. So then it says identify A, B, and C, and then write an equation for the reaction of A with water. So when writing an equation out, write what you know first, and then all the funky balancing stuff, right? And everything else. So I know definitely, it's told you we're reacting A with water, which we know it's CA3N2 plus H2O. Now it's reacting with water to produce, we know that we've just worked out, NH3 and CaOH2. Now we can balance every other element that's easiest to balance, right? 2 N's here, there's got to be 2 N's there. 3 calciums here, there's got to be 3 calciums here. Then I look for what elements are in here that's easiest to balance. Now here there's no hydrogens or oxygen, so I can use hydrogens to balance out how many I need here. I would need 6 hydrogens for you, and then I would need 2 times 3 here, so 6 hydrogens for you. So I need 12 hydrogens, so that's going to be 6 H2O. There you go. So the structure of lactic acid is shown below. Complete and balance the equations for the 2 reactions of lactic acid. So this is your carboxylic acid group. So now that's like immediately like, yo, what's going on? Here we're reacting with sodium carbonate, so write down the formulae first, then you can balance everything out. So Na2CO3 is what we know we're going to be reacting this with. There's a carboxylic acid group here, that's not an acid bit, it's not going to do anything. So one of the products is going to be CH3CHOH, and this will lose a proton, it'll become minus. So it's going to be CH3CHCOO minus Na plus, an acid plus a carbonate makes a salt plus carbon dioxide plus water. Now we can balance this out. So here, if we have a look, We've only got one Na here, but we had two Nas there. So immediately we're going to have two of these and two of those. And then we have Na2CO3 here. There's one carbon here, one carbon here. That's pretty decent. There's 3 oxygens here. And then there's 2 oxygens here and 1 there. And then there was 1, 2, 3 here. 1, 2, 3 here. So the oxygens are fine. So that's it. That's balanced. Done. Now we're reacting with aluminium. So we're, again, write down what you know is going to be. So here, we're reacting this with aluminium. Now, metal plus an acid makes a salt plus hydrogen. So we're going to make H2 gas. We need to think about what the salt would be. So this is Al3 plus, that's going to be an O minus, that's 1 minus. It's going to be 3 of these, but O minus. So CH3, CHOH, COO minus, in brackets, 3 Al, like that. Or 3 plus, really, there. But then as well as that, remember, we've only lost 1 H here, but we have H2 mysteriously there, so we have to balance it, so it's a half there. Done. So the ester methyl ethanoate can be synthesized by reacting a haloalkane with a carboxylate ion. So carboxylate, carbonyl is this, carbonyl, all right? Hydroxyl is OH. Carboxyl is a portmanteau of that word. So carboxyl is C double bond O with an OH. It's in the name. So if it's a carboxylate ion, it's going to be this, COO minus there. And it says the mechanism is nucleophilic substitution. Outline the mechanism for this. So start by drawing the haloalkane, right, that we're doing it with. If it's methyl ethanoate, the carboxylate ion, will have come from the ethanoate part. Ethanoate, carboxylate, right? So this must have been the haloalkane to begin with. So that's going to be C, Cl, H, H, H. They've told you it's nucleophilic substitution. We need to figure out what's acting as the nucleophile. The nucleophile would be this CO minus here because it will have a lone pair. Nucleophiles are electron pair donors. They're attracted to something that they want to give electrons to that are electron deficient. So what I'm going to do is I'm going to write CH3COO minus here and the lone pair's there. Now, when you're drawing mechanisms, think about it as I'm making a bond because electrons are going here and here, and it's all about electron goes here, electron goes here. Don't just draw arrows and memorize them because obviously this kind of stuff happens where you don't know what the mechanism is. If we're doing substitution, that's going to get swapped off because we're making methyl ethanoate. So we need to figure out a way to boot this off. We can't just break bonds without showing where electrons are going. Here, this is a nucleophile. If it's acting as a nucleophile, it needs to donate somewhere. We need to figure out where. Now here, this is more electronegative, so the electron covalent bonds, the covalent bond electrons are closer to here than it is here. So you get a delta positive and a delta negative there. So now we have an electron deficient carbon. This is like, yo, have some electrons, bro, enjoy. But now you've just made a new bond. 1, 2, 3, 4, 5. There's 5 bonds in this. Carbon's like, I need to get rid of something, I'm doomed. The way I like to think of it is that because this is electronegative, the electrons are already closer to this. Then just putting way more electrons into it almost gives it that final push. So what happens is the bond breaks, but you have to show that it's breaking. So the electrons from the bond go to the chlorine like that. What you end up with is you get HCH like this, right? And then it's going to be OOCH3. That's stuck on now. Plus the Cl minus from there that's been nabbed. And that's it, done. So europium reacts with dilute-aqueous acid in a redox reaction, forming a solution and hydrogen gas. The student proposed 3 ionic equations for this, forming europium ions of different charges. Here we go. The student plans to carry out an investigation to determine which one's correct. Hydrochloric acid is used as the source of the H+. So here's their method. What they did is they got a 3 decimal place balance, weighed a suitable container for this reaction, added about 1 gram of europium, and then reweighed. They set up an apparatus for gas collection, add an excess of this acid, measure the volume of gas made, and then they've got these results here. Fine. It says draw a labeled diagram of suitable apparatus for this investigation. We're reacting 2 things together, so we want to collect a gas. In order to measure a gas, we're going to be using a gas syringe. So here's a conical flask. Here's a conical flask in which we will do our reaction, right? And then we're going to have to attach a gas syringe to it like this. But we want to make sure that no gas is being escaped, so we're going to add a bung as well here and make sure that only the gas is going up, right? And then this is probably the worst gas syringe you'll ever see in your life. But I guess you guys can hopefully draw better than I can in this, right? There's your sick gas syringe, right? And there's the things. Just make this a better detailed looking picture, please. My tablet is just really bad to calibrate, that's all. So here, a gas syringe, and it's a closed system because there's a bung there. You don't necessarily have to write the word bung, but the idea is you need to show that it's a closed system so no gas is leaking out anywhere else, which I've tried my best to draw there. So now it says, analyze the student's results to conclude which of 1, 2, or 3 is supported by their results. And it says, assume that the conditions are at room temperature and pressure. So we need to look at each one of these and see what our clue is. So all of these do whatever, right? And what they've done is they've measured the volume of gas produced, and we have numbers for gas. So we need to figure out which one of these gases will fit the bill, right? So if they told you it's at room temperature and pressure, one thing you can do is work out the moles of the gas. because we can work out the volume of the gas that we have from the stuff that they've given us. They've told you that the mass of the container is this and this, and they've told you the volume of the gas is that. So we know it's at least 152 centimeters cubed. It's at room temperature and pressure, so moles of a gas, H2, would equal its volume over 24 decimeters cubed or 24,000 centimeters cubed, which is going to be 152 over 24,000. If we do that, we get 6.33 times 10 to the minus 3 moles, right? This is how much is produced in each reaction, so we can go one by one and figure out how much europium, we would match, if that makes sense, with it. The questions told you as well that we have these masses. We need to figure out what those masses are. It's the mass of europium. So we can work out mass of europium by doing the 33.783 minus the 32.78795, right? And if we do that, we get 0.988 grams, okay? That's how much mass of europium we have. We know its AR is 152, so we can work out the moles of it, because that's how much needed to react to eventually give you this, or how much of this came out from reacting this much. So the moles of this europium is going to be 0.988 over its AR, which is 152, which is 6.5 times 10 to the minus 3. So 6.5 times 10 to the minus 3 moles of europium led to 6.33 times 10 to the minus 3 moles of gas. Can you see how they're roughly in a 1-to-1 ratio? They're nearly the same number. So therefore, whichever one of these has 1 mole of gas and 1 mole of europium is the one that's it. So it's 2. There. So equation 2 is correct. The student repeats this experiment, but then adds concentrated hydrochloric acid instead of dilute hydrochloric acid, and the apparatus gets hot during this reaction. Predict how the hot apparatus would change the results in conclusion in this part. So what we need to do is we have to think about what they're measuring. So here, what they're doing is they're running an experiment, but they're measuring the volume of gas. The question's told you that it's getting hotter. If it's getting hotter, then it's asking you, why might this change the results in the conclusion? We are doing all of this based on the volume of gas. So temperature must have been screwing up the volume of gas. What happens is PV equals nRT, right? V equals nRT over P. If I have a higher temperature, then the volume's going to go higher, assuming everything else is the same. So that means that the gas volume would increase, right? But then we need to think about what could happen here. The gas volume we used here to work out the moles of it. So if this has gone higher, then the moles would have gone higher. So then this would have been higher, and the ratio would have been, bigger. It would have been like 1 to something bigger instead. So then that would falsely tell us that there's more hydrogen made than there was actually in the reaction. So then this would mean the moles of H2 would appear higher, and the ratio of the europium to H2 would be smaller, or the other way around, you could say, or, the H2 to europium would be higher, if that makes sense. Either's fine, as long as you're making it crystal clear that this is higher versus that. So the student modifies their experiment. What they've done is they've got 0.01 moles of europium. They react with an excess of dilute hydrochloric acid, add aqueous sodium hydroxide, and the precipitate forms, right? If we have a look at the original part of this question, all of these reactions with acid eventually make EU ions. Can you see how there's 1 plus, 2 plus, 3 plus? So the precipitate that's formed must have probably been it reacting with the OH minuses here. So we would have ended up with possibly having EuOH, or EuOH2, or EuOH3. So the question's asking you, how could we use this precipitate to figure out which one's correct, right? Well, first of all, we can say that the precipitates will have different numbers of OH minus ions, which means they'll have different masses, right? We need to now show calculation-y kind of stuff, like algebraically how we could do this. There's multiple ways. You could pick one of them and show, or you can say generally what you would do, the steps. So if we have a mass and we want to prove one of those equations are the same, what we could do is we could calculate the MR of the precipitate that should fall, MR of the precipitate, right? So what I mean by that is it would be the mass of the precipitate over the moles, expected, right? If we have 0.01 moles of europium, there's only going to be 0.01 moles of europium in the end. So what you end up doing is you would have the mass of the precipitate divided by 0.01. This would give the MR of the precipitate, and then you can use this to then find out which equation is correct. Obviously, turn that into words, but that's exactly what it is. There you go. So this question's about carboxylic acids. Compound D is a cis stereoisomer of an unsaturated organic acid with this general formula this. A student plans to analyze acid D by doing a titration. So what they do, and I please just write like a little flow chart or just something so you know exactly what's happening. They're supposed to be wordy like this. So 250 centimeters cubed of a standard solution of BaOH2. So we have 250 centimeters cubed BaOH2, and its concentration is 0.15. Then what they did is they are provided with solid BaOH2 and the usual laboratory equipment. So describe how they would prepare the standard solution given quantities, apparatus, and stuff like that. So okay, fine. What we first need to do is we've got to work out how much of everything we need, right? in order to do anything else. Otherwise, we can't really go ahead and, do the rest of this. Here, they've been given solid BaOH2. We need to figure out what mass of BaOH2 we're going to need. All right. So if we want to make 250 centimeters cubed of this concentration, we can work out the moles to make that concentration. So the moles of the BaOH2 needed would be its CV, which is going to be its 0.150 times 250 over 1,000, which means you're going to need 0.0375 moles of this stuff. Now, obviously, we can't measure moles in the lab, but we can do mass equals moles times the MR, which is going to be 0.0375 times its MR, which is 171.3, which gives you 6.42375 grams, right? Which is roughly, well, we can use a high precision balance. Some labs have that, but if we wanted to, we could round it. So then we've at least got the quantity now that we need to make this solution. So now we actually have to talk about how you would make that. So what you would do is you would weigh this 6.42375 grams in a weighing bottle with a high precision mass, electronic balance. And then you don't have to weigh the bottle and then reweigh it after. What you could just do is dissolve it in that, wash it out, and transfer the washings into a volumetric flask as well. That way you're not losing anything. So what we do is then we dissolve it in a small amount of, just double check they're not using any acid or anything here. So it's just water. It's a small amount of water. And then what you would do is you would transfer to a 250 centimeter cubed volumetric flask, because that's what we want to make in the end. Then what we do is we wash the weighing bottle with water and transfer the washings as well into the flask, so we don't lose anything. And then all you do is you fill with distilled water as well, or whatever we're using. So in this case it is water, to the 250 centimeter cubed mark, and invert several times to ensure mixing. That's how you make a standard solution. So the student prepares a 100 centimeter cube solution containing this many grams of acid D, and they titrate 25 centimeter cube samples with this in the burette, and 1 mole BaOH2 reacts with 2 moles of this, and the mean titer is this. Analyze the titration to get 2 possible structures of cis stereoisomers. So there's a lot going on here. Step 1, list again what I was saying before in the previous question. 100 centimeters cubed of 3.125 grams of D. They then took 25 centimeters cubed of D, and they added a sample of D, 25 centimeters cubed, and they added BaOH2 to it. How much BaOH2 did they add? Well, we know its concentration was 0.150, and a lot of people attempted to jump and say that must be 25. Please read the question. It says 25 centimeters cubed of the sample of D, not the BaOH2. The actual volume of the BaOH2 is here, 23.5, right? Cool. So it says analyze the titration results to determine 2 possible structures of this mysterious acid. What we can do is we can work out the moles of the BaOH2. We can then work out the moles of the D in 25 centimeters cubed, and then in 100 we can do mass over MR. MR equals mass over moles, and done. So what we can do here then is let's do that. So the moles of BaOH2 would be its concentration times the volume, which is 0.150 times the volume of 23.5 over 1,000. If you do that, you get 3.525 times 10 to the minus 3 moles. Therefore, the moles of this D in 25 centimeters cubed, please write that. Can you see how 1 mole needs 2 of these? So it's going to be 2 times this. So 2 times the answer we just got. So it's going to be 7.05 times 10 to the minus 3 moles, right? This is in 25 centimeters cubed, but it all came from there. And the question's asking you to find this possible structure from this whole thing here. So the moles of D in 100 centimeters cubed has got to be, so it says in the exam report, I had a look out of curiosity. A lot of people just multiplied by a factor of 10 because they thought it was 25 to 250. And others just put some other random numbers in. It's 25 to 400, so it's going to be 4 times this answer, which ends up being 0.0282 moles. All right, now that we have the moles of D and we have its mass, we can do MR equals mass over mole, which is going to be 3.125 over its moles, which is 0.0282. If we do that, we end up getting 114 grams per mole. That's its MR of what D is. The question's told you that D is what? CnH2n minus 1 COOH. So it's CnH2n minus 1 COOH. So if I just take out the COOH bit, then the CnH2n bit minus 1, is MR, has to equal 114 minus 12 minus 16 minus 16 minus 1. If we do that, we get 69, right? So then to find out how many n's we have, we can do a bit of algebra. So this weighs 12. It's an atomic mass, that's 1, right? So then we'll have 12 times n plus 1 times 2n minus 1, right? If we expand that out, we'll get 12n plus 2n minus 1, and that will equal the whole mass, which is 69. So that means that 14n equals 70. So then n would equal 70 over 14, which is 5. So now we know we have 5 carbons, and we've got, what, 2n minus 1. We have how many hydrogens? We have 9 hydrogens, and we know that we also have a COOH as well. So now we need to figure out 2 possible structures for the cis stereoisomer of organic acid D. So if it is cis transisomerism, then each carbon among the double bonds, has hydrogens on it. Otherwise, it's EZ. But you can use them interchangeably, but when it's cis and trans specifically, you have hydrogens on each. So what I'm going to do is I'm going to draw my double bonds, and it's cis, so the H's are on the same side, right? So C, double bond C, H, and H. The rest I need to just flesh out. So I know that I've got 5 carbons in total, but I've used 2 up, so I've got 3 left to divvy up, and then a certain number of H's as well, and a COOH. So what I might just do is dump an H3C here, CH3, that's done, and then whatever's left. So that means we have 1, 2, 3, so we need to use up 2 more of those, but that extra COH as well, so it's going to be CH2, CH2, COOH. That's one of them. And then what I could just do is I could just have the COOH directly here, and then all of this stuff on the other side there. So then it would be CH3, CH2, CH2, and then you would obviously draw the line a bit more neatly like this. There you go. Those are 2 possible cis isomers where the H's are on the same. This would be the equivalent of a Z isomer, but cis trans is used when they both have an H there. There you go. So penguanine and iodine react in this equation below. A student investigates the rate of this reaction by monitoring the concentration of iodine over time. The initial concentrations are shown here. Nice. So what they do is they then say in this investigation, the order with respect to penguanine can be assumed to be 0. The student plots the graph below to show the experiment results. So why can the order with respect to penguanine be assumed to be 0 in this investigation? All to do with reaction rates, right? Everything to do with reaction rates is 2 things colliding with each other in the right orientation with the right activation energy. Any reaction in the world has to have that happen. So here, if we're assuming that penguanine is 0, remember that an order, when you have an order with respect to something, the concentration of that thing is affecting the rate. As the reaction goes on, these 2 should drop in number as this goes higher and higher. They've told you in the question that this has absolutely 0 effect as the reaction happens, as in, it must be that these 2 are still always colliding. There's always enough of this to collide, meaning that this is never decreasing in this assumption. Otherwise, if you left it to react, this would decrease, and then it gets harder. When you're doing initial rates reactions, you want everything else to be in such a high excess that this isn't limiting the reaction possibly, and this is the only thing that's going down. So the reason here is that this must be never dropping is because there's so much of this compared to that, so that this has always got one of these to collide with to eventually give you that. So the reason here is why can this order be assumed to be 0 is that there is a large excess of pent-1-ene. Now it says, the student's experimental procedure shows that the order of reaction is first order with respect to iodine. Show that this statement is true and determine the initial rate of concentration and the rate constant, and assume that the reaction rate is 0 with order to pent-1-ene, and show you're working on graph and the lines below as appropriate. So what we need to do is there's multiple ways around this. What we first need to do is we need to show that it is first order. So, show the statement is true, and then also find the initial rate reaction and the rate constant. So what we'll do is we'll start by working out the initial rate. The initial rate is the rate in the very start. Here, we've got concentration, and this is, that's concentration, and that's time. On a graph of concentration against time, the gradient would be the change in y and the change in x, which would be the change in the concentration over the change in the time. Would you look at that? The gradient is the rate, right? The gradient can also be described as the steepness. The steepness is kind of steep here, but it's not so steep here. So the gradient is changing because the steepness is changing. That's why we use initial rates, because the gradient or the steepness is different to that up here. So to work out the gradient of this, all you do is you draw a tangent to the point at the very start here, because when you draw a tangent, if I can do it, there we go, like that, right? If you zoom in on there, this curve will obviously be like that, but the gradients here will be nearly identical, in fact the same, at that very niche little tiny point. So what you do is you pick 2 points, this is horrendously drawn, and then you'd work out the change in y and the change in x. So you do y2 minus y1 over x2 minus x1. Now for the sake of time, I'm just going to skip that bit out, but that's how you do it. So the gradient equals the initial rate at time 0, which is why we do it against that axis, which would be y2 minus y1 over x2 minus x1. Let's pretend I've just worked it out. Woohoo, it is 5.5 times 10 to the minus 6 mol dm minus 3. So we've done the initial rate part, right? They've told you what the first order bit is. That's the second task we need to do, and the third is this, but we can do it in whatever order. Now, there's multiple ways of showing that it's first order. So first order proof. If something's first order, then that means if you half like this, this iodine, then the rate should also half. So what you can do is multiple things. You could look for here and half this. If we half that, you get down to here. So you can work, you've got the initial rate here. Then what you can do is you can work the rate out here by doing another gradient. If you do another gradient like that, then you can compare the gradients and the gradient should be half there. Alternatively, in a first order reaction, every time, because, you know, the rate halves each time as well, the half-life will also be the same throughout. So what I mean by that is from here to here, the half-life is the time that it takes to get to half of this thing. So if I do a half-life here, the time in seconds is whatever that value is, which is roughly 2,500, right? So the time it takes for this concentration to drop by half is 2,500. If it's first order, it should be the same. So then if I go from 0.1 to 0.5, then from 2,500 to 5,000, it was also 2,500. So can you see how the half-life is constant? So that's another way of proving it. So there's two ways. There's that or the other way. So I'm going to just say that the half-life is 2,500, and here the half-life is constant. That works for first-order reactions. But alternatively, you can do the other way where you compare gradients over and over and over again. So that's that bit. Now it's just to work out the rate constant. So rate equals k times I, first order. They've told you that, and they've also told you here as well. And they've also told you to assume that the other one is 0. So then to work out the constant, what you would do is k equals the rate over the concentration of I. We worked out our initial rate, so I did quote unquote, here from before, which is when the concentration of I is 0.02. So what you do is you would just do 5.5 times 10 to the minus 6, so I should be S minus 1 up there, mol dm minus 3 S minus 1, all divided by the initial concentration, which was 0.02, I think. Yes, mol dm minus 3. If we divide that by that, we end up getting k to equal 2.5 times 10 to the minus 4. We need to figure out its units. Mol dm minus 3, mol dm minus 3. Those cancel out. You're left with S minus 1. There you go. Done. Alternatively, you could do T half equals ln2 over k. So k would equal ln2 over T half, which would be ln2 over 2,500, which gives you 2.78 times 10 to the minus 4. So further experiments provide evidence that the reaction is first order with respect to both this and this. So what we need to do is rewrite our little rate equation. So our rate equation now is going to be k times I2, it's first order, and then CH3, CH2, CH2, CH double bond CH2, right? Now, when you're doing these rate determining steppy mechanism-y ones, you need to look at the overall equation as well and bring that back into this. So it's going to be this plus I2 makes basically the whole thing but I. So if I just zoom out really, really far, it's going to be, what you should always do is write out the rate equation, because that's going to be the rate determining step, the step that is the slowest, and the reaction can only go as fast as that. Imagine, for example, with medications we do that. So imagine here's a medication, here's a little bit that needs to be broken off before you can actually get to this and use it. Let's say this takes 4 hours to break down. This is like 30 minutes. This can't be broken down until that 4 hours has been done. That's the rate determining step. Until that 4 hours has been done, then you can break this down. So it's a similar principle here. The rate equation has to be the slowest step you possibly can, because that's determining the rate. It's the rate determining step. So the rate determining step will have whatever's in this rate equation as your reactants in the same proportion. So first order means you'll have one of these and one mole of them, right? So it's got to be here. The slow step has to be I2 plus CH3, CH2, CH2, CH, CH2 makes some mysterious thing. And the fast one is, well, everything else basically, right? Now, if you have a look at this overall equation, these two react to make one singular product. At the end of all of these steps, we have nothing else left other than these two are now gone, and this is the only thing made. So you've got to end with CH3, CH2, CH2, CHI, CH2I, right? So we need to think of some mysterious reaction that could possibly happen to make that work, right? This is where it does feel like you're doing a bit of fake chemistry and it doesn't feel too real, but you kind of got to go with it. We have to make some weird intermediate or intermediates that eventually makes this. So what I might do is I might just say that this, becomes positive and this one becomes negative. Pretty decent start, to be honest, right? So what we could end up with is something like CH3, CH2, CH2I, CH2 plus, and an I minus there, possibly, right? So then these two react to eventually give you this. So we get CH3, CH2, CH2, CHI, bloody hell, CH2 plus I minus, and then it gives you this. Because you see that's disappeared now entirely, and the overall reaction is this plus this makes this. That's kind of how you do those equations. You kind of have to just chef up stuff that seems somewhat feasible. And also, as well as that, that's kind of like the electrophilic addition mechanism as well, to be honest. So there's that. So just how this investigation can be modified to show that the reaction is first order with respect to pent-1-ene. So all you want to do is you just want to change pent-1-ene's concentration and make sure everything else is entirely, unaffected. So remember that in the rate equation, we were told that this I2 is first order. So if this equation is going on, that's going to drop. So the rate is also going to drop. We want to make sure that any changes to rate is only because of u. So we need to make sure that that is nearly infinite and will never change. As in, you will repeat, but use an excess of I2, or very big excess really, instead. And what you would do now is if you have a look at their graph that they plotted, it's a concentration of I2 against time. We're not going to do the same thing. We're now going to plot the concentration of CH3, CH2, CH2, CH, CH2 over time instead as well. There you go. So this question's about nitrogen and its compounds. So sodium azide NaN3 has been used in car airbags. The airbag inflates when NaN3 decomposes to nitrogen gas, and there's that equation. It says this is a redox equation, write half equations for the reduction and oxidation processes. So it says write half equations for the reduction and oxidation processes that take place. It's 0, that must have been +1 because sodium tends to be +1 and 0, right? So it's going from +1 to 0 means it must have been reduced, it must have gained electrons. So Na plus eventually becomes Na. In order to have gone from +1 to 0, it must have gained an electron. So there's that one done. If we have a look then, we have N3 here. The N3 whole thing has to be minus because that's Na plus, and there's 3 of them. So you might be wondering, well, how can they share a partial bit of a charge? Well, I mean, that's what the equation shows. I'm going to work with that. If it's gone from N3 minus, it's eventually then become N2 0. So this one step means you've lost 1 electron, right? Thing is that there's 3 N's here and there's 2 N's here. So what I'm going to do is I'm going to balance the elements and see if that might help. So what I can do is I can do 2 N3s, that'll give us 6 N's, and then 3 N2s here. Now if we look, that's gone from a 2 minus E bit to a 0 overall. So that means this will have lost 2 electrons no matter how they were divvied up and whatever. So that means this must be 2E minus on that side. There you go. Just stick to what's in front of you at face value. Don't get too complex with all the other things and thinking about all of these deep things. It must be that the electron was just on one of these atoms within this, for example. So a 16 decimeter cubed airbag is inflated at this temperature. The pressure is this. Calculate the mass of NaN3 that has decomposed to give your answer to 3 significant figures. So we're going to be using PV equals nRT, right? And we need to figure out the mass of this thing. When this is decomposing, it's making N2 gas. So we can find the moles of the gas that's been produced here, right? And then we can work backwards to find the solid of this. So in order to do that, we're going to have to use moles. So moles, N would equal PV over RT. So we need to put the numbers in. So the pressure is going to be 1.2 times 10 to the 5 times the volume, but the volume has to be in meters cubed. This is in decimeters cubed. So 1 meter is going to be 10 decimeters. So then 1 meter squared is going to be, well, can you see how you times by 10 here? Here you're going to times by 100. So it'd be 100 decimeters squared. So 1 meter cubed must be times 10 cubed. So that means you're going to have 1,000 decimeters cubed. So that means in order to go backwards, I need to divide by 1,000. So that's going to be 16 divided by 1,000 to get it into meters cubed. Over R, which is 8.314, times the temperature, which needs to be in Kelvin. So you would add 273 to this, which gives you 290. If we do that, we end up getting 0.7963 moles. Now don't just blindly work out moles, figure out what you just worked out. This is the only gas being made here, so that's the moles of the N2, right? We can see that this is in a 3:2 ratio, so that means the moles of the NaN3 would equal 0.7963 divided by 3 and times by 2. So you can times it by a fraction to divide by 3, because that's divided by 3 and then times by 2. Or you can just do it in steps, either's fine, right? And then you end up getting 0.531 moles. So then we have the moles of the NaN3. We can find the mass by just doing mole times mR, which is going to be 0.531 times the mR of this NaN3, which is 65. And if you do that, you end up getting 34.5 grams there. You should do it to the same number of significant figures in the question, which here is going to be, oh, well, this told you, sorry, 3. Do that. Now it says hydrozoic acid, HN3 is a weak acid with SKa. Calculate the pH of hydrozoic acid. It's a weak acid, so you've got Ka. So the options are you either use Ka equals H plus A minus over HA, or you use Ka equals H plus squared over HA. Now, it's important to just sort of assign letters. HA generally in this context means an acid. H plus is the proton, right? A minus is not the base, it is the salt that's made. The conjugate base of the acid, if you will, if it's weak acids. Because weak acids don't dissociate very far. They're always like, HA dissociates to H plus and A minus. Because they very barely dissociate, these two are practically the same. It doesn't matter because it's like 0.00001 and 0.00002. You can treat them as the same and it won't have too much of a problem. The moment you put a salt into the picture, though, that salt fully dissociates and makes this go up, which is why A minus is the salt, not the base. If we have a base, it's going to be OH minus in this context. That's the base. Here, look at what's in this equation, what's in, what we've been given. H plus is what we want. Obviously, we want H plus. if we want to find the pH. HA is the acid. That's salt. Is there any salt in this question? There is no salt. Is there any base? Well, is there any OH minus in this? No. It may go on to make salt, but there's none here. So then here, H plus we can find, that's what we want. Ka we have, and we have an acid. This is when you work out the pH of a pure weak acid, as in it's a weak acid with nothing in it. So rearrange this first and then put the numbers in. So Ka times Ha would equal the concentration of H plus all squared. But therefore, H plus would be the square root of that whole thing. So then plug the numbers in. So H plus would equal the square root of Ka, which is 2.51 times 10 to the minus 5 times the HA, 0.125. If you do that, we get 1.77 blah 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 times 10 to the minus 3, right? And then you do pH equals negative log to the base 10 of this answer that you just got, right? And you end up getting 2.75. It has to be to 2 decimal places. That's how we write our pHs. When added to water, hydroxoic acid forms an equilibrium mixture containing conjugate acid-base pairs. Complete the equation and then label them. So whenever you're having an acid is something that loses an H+, right? And something that is a base will gain an H+. It accepts it and donates it. Everyone loves saying proton donor acceptor. They don't have a clue what they're saying. The question's told you it's reacting with water, so we're going to add water. Something is losing an H+ this way and gaining it, and the other way around as well. HN3 is probably going to lose that H+, right? If it does that, it makes N3 minus. This has acted as the acid. And it's told you in the question that it is an acid too. If that's losing an H+, something has to gain it. It can't just disappear. So that's gained it, so you end up making H3O+. So immediately, that's acid 1, and that's its conjugate base. But then getting the next part is where people get stuck. Anything in the world that is an acid loses an H+. If this lost an H+, you would have OH-, and that's not here. This can lose an H+, because if it loses an H+, it becomes this again. So that is actually your second acid, and that is your second base. You have to work with the logic that anything that loses an H+, can lose an H+, will be the acid. Anything that can gain an H+, is the base. That's how this theory works. So in the Schmidt reaction, hydroxoic acid, HN3, reacts with carboxylic acids to form primary amines. For example, HN3 reacts with this to form RNH2, and two gases that are found in the atmosphere. Write an equation to show the reaction between this and this. Start by doing the basics, right? So we're reacting HN3. It's easier to do with skeletal formulae, but if you can't, I appreciate it because I do think they're a bit ugly sometimes. 1, 2, 3, so that's 1, 2, 3, 4. Double bond O, OH, and it's 2-methyl, so 1, 2, there's 2-methyl, right? It's going to make something. So the question's told you that if it reacts with this, it will form RNH2. So write down what you know it's going to be. So it's going to be this same thing, but now it's just got an NH2 on the end here, right? And this, then compare side by side. So if we have a look, we're making two gases that are found in the atmosphere. The atmosphere is made of oxygen, nitrogen, CO2, and all that stuff. But even then, what I'm going to do is I'm going to compare them side by side and see what's different. We had a COH here. Now we have an NH2. We haven't dealt with the carbon or the oxygen. Gas that's found in the atmosphere with carbon and oxygen, CO2. We have 3 N's here, but we've only got 1 there. Any gas with nitrogen in, N2. That's how you do that. There you go. Generally speaking, whenever they're like, find an equation for this thing, write down what the question's told you is definitely happening, and you can put the gaps in like that after. There you go. So this question's about 2 reactions of ammonia. Reaction 1 says excess ammonia is reacted with 4.77 grams of copper oxide, and this reaction makes this much solid E, liquid F, and 0.560 grams of gas G, which has a volume of this at room temperature. And then reaction 2, ammonia reacts with compound H to make I, which is C2H5NO, and a chloride salt J, and the IR spectrum of I is shown. Right, what we need to do first is we've got to have a look at this step by step, because people love to go and mix everything up, mix and match, and just completely lose where their focus is, and just screw up everything. You have to do it bit by bit. Generally speaking, the order they tell the story is a pretty good order to follow. So let's look at the stuff they've given us. They've told us that we have this massive G and we have a volume of this at room temperature. So with G, it's a gas, right? So moles of a gas would equal its volume over 24 decimeters cubed, or 24,000. We could find out the moles of G, couldn't we, using that? So it would just be 480 over 24,000. If you do that, you get 0.02 moles of G. Now, they've told you the mass of G, so we could work out its MR of G. So the MR of G has to equal mass over moles, which would be 0.560 over 0.02. If you do that, you end up getting 28 grams per mole. Now, G came from reacting excess ammonia with copper oxide, right? The gas that it's probably going to be is N2, which has an MR of 28. So that means that G has to equal N2. Cool. So now we know that we have this much copper oxide, so we can work out the moles of this CuO as well by doing its mass over its MR, which is what, 4.77 over the MR of CuO, which is going to be what, 63.5 plus 16. If we do that, we end up getting 0.06 moles. All right. So for some reason, if you look, this amount of this reacting with ammonia makes this many moles of G, as in CuO plus NH3 makes some mysterious amount of N2. Can you see how there is 0.06 here, and there's N2 there, and that's going to be 0.02. There's 3 CuOs for every one of them immediately. Fine. If we then have a look, what else can we find out? Well, if you look at E is a solid, right? And we've got this many grams of that solid. So what I know is that whatever these moles must have been must have eventually gone into the solid, right? So that means the moles of this would eventually be the moles of the solid. So the MR of the solid would equal its mass over its moles, which would be 3.81 grams divided by the moles that it must have come from. It all must have come from here, which would be, where's it gone? 0.06. If you do that, we get 63.5. That's actually the mass of copper. So now we know in our equation 3CuO plus NH3 makes N2 plus Cu. So we need to figure out what this other mysterious thing is. So this is lost in oxygen, this is lost hydrogens, the other thing it will have been is probably water. So then if we balance this, 3CuO, there'll be 3 H2Os there, so there'll be 3 Cus here, and then how many, that's 6 H2O3, so we need a 2 there. So then we've just figured out what E, F, and G are. E is going to, so F and G. E has got to be Cu, F has got to be water, the liquid, because they told you it's a liquid we made up here, and G is N2. So we've at least done that part. Let's look at this IR spectrum then. Ammonia reacts with mysterious H and it gives you this thing here, I, and it's got C2H5NO and some mysterious chloride salt. The IR spectrum is shown below, so let's go bit by bit and see what we see. If we have a look, we can see there's a dip like kind of around here. So if you look at our data sheet, what matches this range? It's about from there to there, which is about what, 3,100 to 3,700. If I have a look at my data sheet, so if you have a look at this spectrum, there's all these mishmashy bits of peaks, right? But some of that's going to be CHs. So if you look at where, like, if you look at the CH in the data sheet, it's 2850 to 3100, right? That's kind of like where, to like about there. So all of this mucky stuff is probably that CH. So the next peak that comes after that is all of this bit here. I usually draw a line or like put my ruler down where it goes down, if it would freaking let me, like that. And then I'd work out that. So that's what, 3,200, 300, 400, 500. It's like 3,200. So you'd say there's a peak of like 3,200 to 3,500. And if we look at our data sheet, that fits most likely NH, right? And as well as that, you know it's C2H5NO. So we're going to look for something with N in it. Then there's an O in it. We need to go look at where that oxygen could be used. So in your data sheet, you have COs, which are, you know, alcohols, esters, carboxylic acids, but they're in the fingerprint region, so they're really hard to tell apart. It could be OHs, which is massively broad, but that's not here, or it could be OHs from like phenol and stuff as well, or it could be C double bond O. In the C double bond O in the data sheet says it's 1630 to 1820, 1500, 1600. Wow, would you look at that? There's a peak from here to here. That's in that range. So then there's a peak at 1600 to like what that, 1717 like 50 roughly, right? Which fits the bill for C double bond O. All right, so we know what's in this now. Ammonia, so NH3 plus some mysterious thing ends up making C2H5NO and some chloride salt J. Fine. Where on earth does the chloride come from? If you can see here, we have C2H5NO. We've got a double bond O and an NH. C double bond O, NH. We have made an amide. So we need to think NH3 plus some mysterious thing with this in it eventually made an amide and a chloride J. The original thing must have been an acyl chloride, which means the original thing must have been, where's the chloride bin? The original thing must have been an acyl chloride. So then it would have been C, like on its own, just chilling, so CH3, and the acyl chloride, remember, a C double bond O Cl? So then it would be CH3, COCl, plus the NH3, gives you this thing, the amide, and J must be, well, we had a Cl minus left over, it must have reacted with that to make the salt, so NH4Cl. And if I balance that, well, we've got to put an N in here and the extra H's in there, so there's going to be a 2 there. And there you go. I think that's balanced. So then, H has got to be this acyl chloride, CH3COCl. I has to be, well, I is that, but actually we want like the actual structure of I, rather than just writing the same thing they told us. So the actual structure of this thing is going to be CH3CONH2, amide link now instead of this. And then J would be NH4Cl. There you go. Thank you very much. I hope that helped. Please like, share, and subscribe. You know the drill.